Good afternoon. Oh, wait. It's too strong. So my name is Roberta Zambrini, and I'm from IFISC in Mallorca. What is on my computer? Okay. And from the from the Institute of Cross-Disciplinary Physics and Complex Systems. And the work I'm going to show today is in collaboration with these guys. No? Sorry, just a second to get acquaintance with it. Okay, with this guy. And the talk of today is about spin synchronization. There's a bit of a change of topics with respect to what we have been listening before. So the phenomenon of spontaneous synchronization is a phenomenon that is well known from Huygens, that was the first person reporting on this phenomenon centuries ago, a couple of centuries ago. And this phenomenon is related to the possibility of systems that are different between them to adjust their dynamics and to start to evolve in a common way. If they are oscillator, they will start to oscillate at the same frequency. They can be chaotic systems. There can be a very large degree of disorder in these systems. And this is a phenomenon that is being largely observed in natural systems, going from biological systems to chemical systems. So this is, for instance, a well-known example of fireflies. They start to flash randomly at the beginning, and then you can observe really a synchronous flashing of their, a really synchronous dynamics, sorry. And more recently, in the last, let's say, 10 years, there have been several works trying to extend this phenomenon from the classical regime, where it is well known in different forms, to the quantum regime. And these are, for instance, nanomechanical oscillators that are one of the system, an example of a system they are susceptible to be observed in a quantum regime and displaying synchronization. So the aim of this talk is to give an overview a brief overview about this subject, and then to present some results about synchronization in spin systems. In particular, I will show something about the possibility of relate synchronization with superradiance, and then the possibility to use synchronization for probing, and finally, some preliminary results about synchronization in optical lattices. So the first study of synchronization, we're actually dealing with entrainment. So entrainment is a phenomenon in which you have an external driver, and the system starts to oscillate synchronously with the external driver. And it is opposed to the phenomenon of spontaneous synchronization, in which you have different systems, and they evolve in their dynamics and spontaneously go towards a common framework dynamics. The case of the phenomenon of spontaneous synchronization can be studied now in different systems like van der Pol oscillators, spin, complex network, optomechanical system, atomic clouds, and so on. And experimental, these are all theoretical work, so there are still few things about experimental observation of quantum synchronization. And one point I would like to do is about what is quantum synchronization, related to the fact that actually synchronization typically is a classical phenomenon that is related to trajectories and to the observation that you get some similarity in initially different trajectories. So a first point, of course, a fundamental issue is just to define this phenomenon in quantum framework. And actually, due to the fact that there can be different approaches to this, there have been also different suggested measures for synchronization. And for instance, the first approach we took was just to consider synchronization related to the local observables. So look at the dynamics of local observables, and if they get a common dynamical behavior, then to speak about synchronization. This approach allows to distinguish, to define synchronization, and then to compare it with quantum correlations. A different approach can be taken considering instead forms of correlations as a measure of synchronization. This, for instance, was the approach taken here, in which they were defining something that is similar to what classically was called a synchronization error. So here you actually have a definition of a correlation to define if these fluctuations are small in this variable, then you can say that the oscillators corresponding Here Q minus will be, for instance, Q1 minus K2, so the difference in position and the difference in momentum. If these fluctuations are small in this difference, then you speak about synchronization. So and so on, you can define different measures. Here we have, in a book chapter in this book, you have been reviewing these. And of course, you can just look at the dynamics. You can look at the spectral components of your dynamic and see if out of different frequency, by tuning some parameter, you actually have a dynamics in which just one frequency is remaining present, and you speak about synchronization. Or you can look at localization in the Wigner function, so you see there is a large variety of approaches. And also, you can define out of all these measures of synchronization, how you can define what is really a degree of quantumness of quantum synchronization, looking at the number of non-commuting variables that actually do synchronize. So this was just a brief overview of what you can define as quantum synchronization, and now we will move in considering what are the origin of quantum of synchronization in general, actually. The phenomenon of synchronization is really widespread. So I mentioned you can, so for instance, the swaying of the Millennium Bridge is a phenomenon of synchronization, and the same phenomenon of synchronization is what is in our brain or in the cells of our heart. So it's a really universal phenomenon that is paradigmatic actually in complex systems. And in most cases, synchronization is related to the fact that actually you have units that are coherently interacting between them, and this is giving rise to synchronization. But it actually is also possible to synchronize objects considering different forms of dissipative coupling. So different units can interact with an environment, and it can actually be the shape of the environment determining the presence or not of synchronization. And we have been considering this kind of dissipative coupling in different systems, and this kind of dissipative coupling arises, for instance, when you have collective dissipation. And collective dissipation is, for instance, what is the basis of superradiance, when you have atoms that are emitting light and they are nearest than the emitted wavelengths, then you have the condition for collective emission. And you can have also collective emission in a structured environment. So this would be the case in which you have atoms nearest than their emitted light wavelengths, and this is as well known, it was reported by Dickey in 1954, the situation in which you actually have collective emission. But you can actually have even units that are far apart, and still you can have collective emission. This happens, for instance, when you have units that are interacting with a structured environment. Here, for instance, you can have two units that are interacting with a lattice environment. And in this case, even if the two objects are far away, if they are tuned with the proper frequencies, then you can observe collective dissipation taking place. So for instance, here you can go as a function of the distance between the two emitters. You can have a situation in which you have collective emission in black and independent emission in, collective emission in white and independent emission in black. And you will have situation in which by taking the two units apart, you will actually start to dissipate independently, as one would intuitively expect. But in other cases, if the frequency of the system is high enough to actually see the structure of the environment, it can happen that actually, depending on the position, you can actually have even units that are far apart will feel common dissipation effect, collective dissipation. And you can even have a strange situation in which you can actually have on the top of a lattice directional coupling. So the presence of collective dissipation only in some particular direction. And we have been exploring this in some recent works. So the possibility of having the form of the dissipation determining the presence, the emergence of spontaneous synchronization, we have explored this possible phenomenon in harmonic oscillator systems, in particular considering them in complex networks. So there the question was, given a complex networks, it is possible to observe, in spite of the diversity of the units, some units that start to actually oscillate synchronously, and we actually shown the possibility of this behavior, and not only the possibility of observing it, but also the possibility to tune the whole system to synchronization just by changing the frequency of one of the oscillator. And this was a work a few years ago. And we have actually seen that the mechanism behind this synchronization is the fact that you have the dynamics of your system that is that is governed by different components, but the presence of a structure in the dissipation gives rise to the fact that you have some modes that dissipate slower than the other. So the presence of a least dissipating mode gives rise to the possibility of having synchronization. This possibility has also been explored in case of spins, and it was actually observed that two spins interacting with an environment, they can actually evolve towards a synchronous oscillation in spite of their diversity, and that this phenomenon really needs the presence of dissipation. Dephasing is not enough to give rise to this phenomenon. So these were previous results, and now I would like to show some recent observation about the relation between synchronization and superradiance. So just a reminder of superradiance. So superradiance is, as we said before, you have atoms that are nearer than the correlation wavelength. Then you have actually a burst in the emitted light that is very different from the case in which you have the independent emission of the different atoms. This was observed after the initial prediction. It was observed in the 90s, in 82 actually, and there were, after the initial experiment in micromeasure, there have been several more recent experiments showing actually superradiance also in systems with ions, artificial atoms, circuit QD, and cold atoms in these alligator photonic crystal configurations. So the possibility of observing this phenomenon is now well established, and our aim was to see which is the relation between this phenomenon, so superradiance, and the fact that you can actually have spontaneous synchronization. In order to understand the connection, the first things we need to do is to take superradiance to the ground in which you study synchronization. That is the case in which you have units that are different between them. Typically, superradiance here is considered between identical atoms, so the first things you need to do is to introduce some detuning between the atoms and to revisit the phenomenon. This was what we did here, so we consider two spins with some detuning between them, and then we analyzed the effect of superradiance considering within a standard treatment the dissipation of this system between Lindblad, Gorini-Kosakowski, Sudarshan master equation within the standard approximations. So what we find is actually by using a Lindblad representation that is particularly nice for this problem, you can actually get analytical results. And you can actually observe that in presence of detuning, you have somehow changed situation with respect to the identical atom case. In the case of the two spins that are detuned, you will have 4 levels for the composed dynamics, but you will have something that generalizes the symmetric and the anti-symmetric state that you have there. They are simply not degenerate in this case, and they again define the superradiant and the subradiant states, in which actually you have, for the superradiant states, you have a larger decay rate, and for the subradiant states, you will have a slower decay rate. Everything can be actually calculated analytically, and this is important in our case because it actually allows not only to re-explore the phenomenon of superradiance, but really to have an exact relation with the phenomenon of synchronization. So first of all, we just see here, in presence of detuning, you still have some modes that really evolve very slowly in time, so this will be just a simulation of the system, and for some other, you will have a very fast decay, while you see for independent atoms, you have typically the intermediate behavior. So we can now compare superradiance with synchronization, and actually what we observe is that if you now look at the dynamics or the local dynamics of these two spins that are detuned between them, typically you have initially some dynamics of the two spins that can be more or less complicated depending on the parameters that you choose. But after some time, you actually observe that the two spins evolve in a synchronous way, and actually in this system, synchronization is a time delay synchronization. So you can have some delay between the two trajectories that you need to take into account. So the two trajectories are still synchronous, but you need to delay one of them, and this can arrive to the maximum possible delay in which you have anti-synchronization, or it can take intermediate value. You can also calculate these kind of things. So the main point about this analysis is actually that in this situation, when you actually reached the synchronization, what's surviving to your system is the coherence between the subradiant mode and the ground state. So really, the synchronization that arises in this system can be traced back to the coherence between the subradiant modes and the ground state. And this is a nice way to make a connection between the two that is allowed because you have actually the possibility to look analytically at the problem. So actually also the time scale in which synchronization arises is related to the time scale in which only the subradiants remain present into the system. This is another way to say the same thing, to sell the same message, in which you see actually that if you look at the presence of synchronization and of the subradiant radiation, you actually find that going from independent dissipation of the two atoms to collective dissipation on this axis, you actually have a rather good agreement between the behavior of the two quantities. So the take-home message about this part is that by using a full analytical approach, you can actually establish a connection between subradiance and synchronization, and in particular, we have seen the synchronization is related to the presence of this coherence, the long-standing coherence. And another thing is that actually synchronization is something that we have defined and looking at really local quantities, because we have been just looking at the local observables, while synchronization, while superradiance is really a collective behavior. So the fact of having synchronization taking place and being a signature of subradiance actually also means that you can look at local observable to get insight about the presence of a collective phenomenon. So I will now move to the second point, that is the possibility for using synchronization for probing. So in this case, we imagine a situation in which you have a system that is less accessible experimentally. So it can be, and in our case, is a dissipative qubits. It can be, for instance, an ion that has a characteristic for which measuring it is not so favorable, and you are actually accessing an external probe that is attached to this one, okay? So in our case, we have the system that is our dissipating qubit, and then you have an external different qubit that is our probe. And we are interested in probing the features of this qubit that are this frequency, and as it is an out of equilibrium system, the form in which it is dissipating in its environment, okay? So we consider this kind of setup, and in this case, it can actually be shown that in this case is different from the previous one. Previously, we had collective dissipation. Now, instead, we have dissipation taking place only in one of the two units of our system, but still also in this setup, synchronization takes place, okay? So here you have synchronization, and actually the dynamics of the probe and of the system that you are probing, depending on the frequency of the probe, they can get synchronous or anti-synchronous. So you have actually the possibility to observe both behaviors. So here we are using this indication that is just measuring the correlation between the Cmax dynamics, and when it is equal to +1, it will tell us that we have synchronization, and to -1, you have anti-synchronization, so just in antiphase, and it will go to 0 small values when you do not have any synchronization at all in your system. So here, depending on the frequency of the probe, you can actually have both different behaviors. Here we just show how tuning the frequency of the probe, actually you go from anti-synchronization to synchronization, and actually looking at the spectrum of the probe that is oscillating in times, from the spectrum you can actually recognize that, for instance, here where it is anti-synchronous, he will develop after a transient time just one frequency, that is the frequency toward which it's synchronizing with the system, and then by changing the frequency on the probe, you just go to the different frequency into the dynamics. The transition of the synchronization and anti-synchronization is continuous, but the frequency of the probe itself actually exhibits a sudden jump. This sudden jump is shown here, and actually moving the frequency of the probe, one can get the first insights into what is needed to be measured to probe in the system. So you need to measure the frequency of the system, to infer the frequency of the system, the coupling between the system and your probe, And then you want to explore which is the form of the dissipation of this system. So what you have here is actually from the measurement of this frequency before in the regime of anti-synchronization and after the jump in the regime of synchronization. So from these two values, you can actually infer both the value of the frequency of the system and the coupling with it. So this is the first part of what you need to measure. Once you have the frequency of your system, it is actually known, you have derived the frequency of your system, it is actually possible to derive also the form of the out-of-equilibrium dynamics of it, determining the features of its environment. So for a dissipative system, the description of the dissipation is embedded in our case, in the spectral density of the problem. And the spectral density for typical problem can take, for instance, ohmic, superohmic, or subohmic appearance, depending on the relation, the power relation of the frequency. So if S is equal to 2, 1, or minus than 1, you actually go from superohmic to ohmic to subohmic. The point is that actually the frequency jump that you observe here depends on the features on the environment. And this is the feature that is exploited in this scheme to infer which is the form of the environment. So in this case, we are just assuming that the environment is a power, and then you can infer by the position of this jump which is the value of this power. So you are able in this case to complete your task. And actually this prediction there is obtained by analytical description of the problem, but if you just look at the dynamics of your system, you actually find good agreement. So this would be you tune the frequency of the probe, and you actually see that as a function of S, this is moving, and the analytical and theoretical prediction are in very good agreement. And this can be generalized also to generic shape of the spectrum. Is a little bit more complicated, and you need to do different measuring, which you can actually vary the values of lambda, but you can actually rebuild arbitrary shapes of the spectrum. So this is the way in which you can actually use the transition of synchronization in a regime in which you have synchronization and then a sudden jump to anti-synchronization in the frequency of the probe to actually infer the features of your out-of-equilibrium system. And the possible implementation are, of course, in different systems with ions, with qubits, and with cold atoms. So the last things I would like to show are some preliminary results about the possibility to observe synchronization in atomic lattices. In particular, we are basing our description on the model that has been introduced here. So in this work, Schwanger, Sirac, and Gidke were actually considering a configuration in which you have your lattice, and in each site you actually have a 3-level configuration, and the two lower motional degree of freedom of your system. And by proper tuning of the frequency in your lattice, you can actually map this system into a dissipative model for spins. So this is quite powerful because it allows to actually get dissipative spin models in a platform that you can use to do quantum simulation of this form. So we are really considering now this system, and moreover, on the top of it, for the purpose of analyzing synchronization, we are considering the case in which the lattice is not a uniform lattice, but it is a bichromatic lattice. So in the presence of a bichromatic lattice, you will actually have a dimeric configuration for the spins that you put into your system. So now, the two-level system are just the two motional degrees of freedom of the atom on each site, and you actually have a description of your system in which the Miltonian parts take into account the detunings between the two possible configurations, so the two kinds of atoms, of two-level systems that you have, and there is only one species, so the tuning is just due to the bichromatic character of the trapping potential. So here you have this detuning, and in this system, the detuning constrains also the form of dissipation. So in this case, you will have one of the two-level systems, the odd site with some frequency and some losses, and then you will have the tuned value in the even, for instance, sites. So this is the platform we are going to consider. And again, also in the system, there is no collective dissipation, but there is an important thing that is the imbalance between the dissipation between the two. And this imbalance is actually able to lead to synchronization. The first thing that we look is the case of 2, because in that case we have analytical results. And what we actually found is that in presence of 2 spins, you can actually observe a synchronization in this case. And you can have synchronization actually in all the variables. So this would be, for instance, an example of complete synchronization, because you actually have synchronization in all the observables. And there is a strange feature of this system that is typically in a system, classical or quantum, you have that synchronization can emerge if the coupling between the units is big enough, and it's typically happening when the tuning is small. So when you increase the detuning, of course, the diversity between the units of your system, typically you lose synchronization. But in this setup, actually, you have something that in principle is a bit counterintuitive, because actually the synchronization increases with the detuning. So in this map, we have plotted the detuning and the coupling between our pair of 2-level systems, and we actually see how the synchronization is actually improving with the detuning. So in principle, in spite of having not collective dissipation, but an unbalanced dissipation into our system, we can get synchronization out of it. And now we try to move to larger configuration to see if this synchronization persists. What we actually have is that synchronization in presence of 4 2-level systems is actually remaining present into the system and takes different form. So depending on the parameter, you can have the synchronization exhibiting different patterns. You can have synchronization between the external pairs, but anti-synchronization between them, or different scenario in which only the one with the same initial frequency synchronized. So you have actually different form of synchronization. And again, there are several cases in which the synchronization is complete because you observe it in all the observables of your system. So moving towards larger spins, of course, it becomes quite demanding. So it's something that we are trying to treating analytically by introducing some approximation in the dissipative form. When you consider the system, by the way, has been on everything, taking a Jordan-Wigner transformation, and then you can really look at the dynamics of the components of your system. And this is still work in progress, but in general, what would you expect is that in this same configuration, if you go to larger configuration, you expect to lose actually synchronization, because the mechanism that is behind synchronization in all this system is the fact that you introduce some separation between the time scales of the dynamics of your system, so something at the end remain present because the dynamic of this mode is gapped with respect to the rest of the states present, but increasing the number of components, this effect could actually be lost. And then at that point, it would be interesting to explore different configuration instead of the dimer to see the synchronization can remain present. So summarizing, what we have seen is that the phenomenon of synchronization that has been vastly studied in classical system can be considered also in quantum system. There are a plethora of systems that exhibit this problem, this phenomenon, and a common feature in a part of this system is that the form of the dissipation can really have a key role, and we have shown examples in which the form of the dissipation is actually essential. In fact, in all these examples, if you move from the cases that we have considered with collective dissipation or imbalanced dissipation to a scenario in which the dissipation is just independent in each unit, but you will actually lose a synchronization. Synchronization will not appear. So we have described different forms of, let's say, dissipation-induced synchronization, and we have seen that this can be connected to the phenomenon of superradiance in the case of the tuned system, can be used for probing, and we've shown some preliminary results about the possibility to observing it in optical dimeric lattices. So thanks for your attention. Here there are a few references and just some publicity about a workshop that will be in weeks in May in Mallorca, the Central European Workshop on Quantum Optics. Thanks for your attention.
thank you for a wonderful talk and bringing us into this other area of the workshop. I really appreciate it. I am very curious to hear your thoughts about the connections between the synchronization problems that you're looking at and this other field of study, which you probably have heard about, called quantum time crystals.
Quantum?
Time crystals.
Quantum time crystals.
Yeah, because they bear marked similarities in their thought process, and I'm curious if you think that there's depth to be explored there, or if it's a trivial connection, and if of course you prefer not to comment, I also appreciate that as well. But I'm just very curious.
One can imagine a setup in which you can actually put the two things on the same ground, so you could. And in what I see, time crystal at the end is a behavior in which you have some regularity in time that is a feature that is really widespread in classical dynamical systems. So I would expect that you can actually use also that framework to study synchronization between these. I mean, it's a possible and definitely timely research to pursue.
Thanks. How does the synchronization depend on the interparticle coupling strength? Do you have to have strong coupling, weak coupling?
No, it depends. For instance, in the case of SUBRADIANCE, actually the units are not coupled at all. The only coupling comes from, in a theoretical framework, it just comes from the small lump shift that you have coming from the interaction with the environment. But initially, you do not have any direct interaction between them. It just comes through the environment, so it's typically small. So in a simpler setting, you need to have the coupling to overcome the detuning between the units. But in more sophisticated setting, like in these cases, actually this is not always necessary. If you have this mechanism of synchronization, that is that you have imbalanced losses, and these give rise actually to helping synchronizing your system, this happens with not necessarily the need of a strong coupling between the units. So it's more...
So in one of the first systems you show where you have two probes to the same kind of path, to the same lattice, can you say something about if there is appearance of entanglement between the two probes, and if it's related?
If there is any?
Appearance of entanglement between the two probes, and if it's related to synchronization in some way?
Yes, some entanglement can arise in these cases. If you have only the dissipative coupling arising between the systems, then it will be small, because in any case you have a very small coupling that appears in between the units, and then it's small. But we are actually looking into another case in which the form of this structural environment can also be used to introduce coherent strong coupling between the units. This is a work in progress, and in that case you can actually induce a larger entanglement. Then, of course, in all these cases, what you have is that the system, if you put entanglement by hand at the beginning, entanglement will survive longer. That's definitely true. But the possibility to actually induce entanglement in your system through the environment, it's something that is more difficult to achieve.
Okay, if there are no more questions, then let's thank Roberta.
Thank you.